Okay, welcome everyone. So, it's my pleasure today to get to introduce Professor Yiling Chen. Yiling is the Gordon McKay Professor of Computer Science at Harvard University. I had the great fortune of being her Ph.D. student, so that gives many of you a sense of her patience and kindness. If you needed any more evidence of that, she's been the program co-chair for a number of important conferences in computer science, and most recently AAAI 2023. Wow. Yiling has received a number of awards for her research, including Best Paper Awards at conferences like Economics and Computation and others. She works on topics often at the intersection of economics and computer science, focused on societal impacts of computer science and computation. Today, we're going to get to hear from her about strategic design to improve information integrity. So please join me in welcoming Professor Yiling Chen.
Thank you so much for the introduction, Bo, and thanks for having me here. So Boulder feels very special to me, and I think mainly because of Bo and Raf here. So it's my pleasure to be able to come here and visit. Today, I'm going to talk about some of our effort on improving the quality of information. So a line of research that my research group has been focusing on over the years concerns the issue related to information integrity due to that data or information are contributed by humans, and humans can act strategically. And just to give you some example of the type of work that we have been working on. So we've been interested in like eliciting high quality information from people. So for example, in surveys or online reviews, how can we get the truthful information or the high quality information from individual participants who are sharing their information with us? Or even that the reported data, for example, the COVID case number that people collected from different sources, how can we ensure that those data are reliable? And for this line of research, we typically try to design incentive mechanisms such that it is to the best interest of the participants to exert effort and reveal their best information. And we're also trying to quantify the value of the collected information, even if we can't really directly verify the quality of the information using the ground truth. So mostly because of the ground truth is not reliable. And more recently, we have been working on how can we design some tests to determine whether data source, the data coming from a data source is reliable or not. And I guess the second line of work, we've been thinking about the incentive issues in the context of machine learning. So when we're thinking about machine learning as a decision rule and data are contributed by individual agents or entities, then any decision rule are going to solicit a strategic response. So along this line, we've been thinking about questions like, how can we design learning algorithm, be aware of such potential manipulation of the individual agents when they're contributing to data, and how can we make such type of algorithms to be more robust toward the strategic behavior? And a third example is the spread of misinformation on social media platforms. So we all know that social media platforms concerns about the misinformation. And when the misinformation are widely spread, so that's going to just cause more harm. And along this line of work, we've been recently thinking about how can we take a softer approach, so in the sense of like dissuading the users to not share misinformation. And today I'm going to really just focusing on this line of work. I will be talking about a recent paper that we have trying to think about how can we persuade agents to not share or reduce the sharing of misinformation. As we all know, misinformation has become a problem. So This is a survey from the Field Research Center. As you can see that the survey response over the years has increasingly feeling that both the US government and the tech companies should take steps to restrict the false information online. Okay? And a lot of times the social media platform are going to do some interventions with the hope to reduce misinformation. And one type of intervention can be just tagging a post with a tag saying that, oh, this potentially can contain misinformation. But at the same time, even if when people are really concerned about and thinking that we should find ways to reduce misinformation, there is a concern of freedom of information. So, but the trend is quite interesting over the years. As you can see that back in 2018, 58% of the survey respondents think that the freedom of information should be protected, even if that means false information can be published. And last year, 2023, 42%, which is still a significant percentage, but it's much less than the 58%. Only 42% of the survey respondents are thinking that the freedom of information is more important than preventing the spread of misinformation. But this percentage basically thinks that people still value the freedom of information, the freedom of speech. And this suggests that we actually should think about whether there are softer approach, less intrusive approach in reducing misinformation. What I'm going to talk about today is our recent work on a persuasive approach to combat misinformation. This is a joint work with Stefan Hosing, who's at Harvard, and Angela and Garcia, both at Miller in Canada. So what we're trying to do is we're taking an information design approach, trying to reduce misinformation. And let me explain what information design means. So information design really just meaning that we're trying to design the informational environment for an agent to influence the belief of the agent such that the agent's decisions are going to be affected. And information design usually is an agent with some informational advantage will decide strategically what information to reveal to another agent with the hope to influence their belief and then influence their behavior. So in this setting, there necessarily needs to be an agent who has more information. And the agent with more information can strategically decide what information to reveal to another agent and such that the other agent can be influenced. So that's the general information design approach. And the most classical example of information design is Bayesian persuasion. So this dates back to the classical paper in 2011 that first introduced the problem of Bayesian persuasion. So I want to really illustrate the Bayesian persuasion using the example that was given in the original paper and try to give some insight about why changing the information environment of an agent can potentially influence the agent's behavior. So this example has two agents. One agent is the sender, the other agent is the receiver. And in this example, we think the sender is a prosecutor and the receiver is a judge. And then there are some defendants. And there are some true state about the defendant. And the true state here is binary. Either the defendant is guilty or innocent. And the judge, who is a receiver, can take one of the two actions. So the actions are acquit or convict. So make decisions on the defendant case. Okay? And both the sender and the receiver have their own utility function. And usually the Bayesian persuasion happens is because the sender and the receiver's utility functions are not perfectly aligned, as in many real-world scenarios. So the prosecutor actually doesn't really care about whether the true state about the defendant is guilty or innocent, the sender will receive a utility of 1 regardless of the true state, but as long as the judge's decision on the defendant is convict. And otherwise, the sender will receive utility 0. And the judges, being a really great judge, cares about justice. So the judge receives utility of 1 only when he makes the right decision. And the right decision means that if the true state of the defendant is guilty, he made the action of convict. He takes the convict as his action. And if the true state of the defendant is innocent, then the judge takes the action of acquit. So only when those 2 scenarios happens, the judge receives utility of 1, and all other scenarios, the judge receives utility of 0. Okay? As you can tell that in this case, the sender and the receiver's utility are not perfectly aligned because the prosecutor would prefer the judge to actually take the action of convict, even on a defendant who's innocent. Okay? And we usually assume in this setting that our agents are all Bayesian agents, so they're fully rational. And there's a common prior on the likelihood of the defendant being of the state of guilty. So there is a prior distribution. And in this case, the prior for the defendant having a guilty as the true state equal to 0.3 with probability 0.3. Okay? And the prior is known to both the sender and the receiver. Okay? So far, no one has any informational advantage. But suppose after some investigation, the prosecutor will actually know the true state of the defendant. So the prosecutor will eventually know whether the defendant is guilty or innocent. And then let's look at some scenarios about the decision that the judges can make and the corresponding sender and the receiver utility. Okay? So the first scenario is without any communication. So without any communication, the judge will make his decision based on the prior, because the prior basically says that most likely the defendant will be innocent. And since the judge's best action is to always take the action of acquit, so because there is no other information, and then the sender's expected utility in this case for the prosecutor who really only receive a positive utility when the judge takes the action of convict. So the sender's expected utility is 0. And the receiver's expected utility is 0.7, because with probability 0.7, the judges make the right decision. That is, with probability 0.7, the defendant is actually innocent, and acquit is the right decision for the judge. So that's without any communication. But now think about the prosecutor actually have some additional information. So the prosecutor has the information advantage. And what the prosecutor wants to do is the prosecutor wants to influence the judge's decision to increase his own expected utility. And what does influencing mean? So influencing is really saying that as the prosecutor, I hope the judge would take the action convict more frequently, because that's the only way to increase the prosecutor's expected utility. So how does this going to work? So the sender can, before seeing the true state of the world, can commit to what we call a signaling scheme. So the signaling scheme basically saying that, so given the true state of the world that I have observed, I'm going to, with certain probability, send a signal or a recommendation to the judge. So in this particular case, this is a fully revealing signaling scheme because the probability of sending a signal C or a recommendation C, you can think about this as the prosecutor recommend the action of convict. given that the true state of the word is guilty, equal to 1. So meaning that whenever the true state is actually guilty, the prosecutor will recommend the judge to take the action of convict. And whenever the true state of the word is innocent, the prosecutor are going to recommend the judge to take the action of acquit. So in this example, the sender reviews full information to the judge. And judge, knowing the signaling scheme, will make the right decision. So whenever the sender recommends convict, the judge will take the action of convict. And whenever the sender recommends acquit, the judge will take the action of acquit. This is because of the judge essentially in his head will be calculating the updated conditional probability of conditioning on receiving a signal, what's the probability for the true state being guilty versus what's the probability for the true state being innocent. And in this case, both equal to 1. So the judge essentially knows the true state of the word, just as the prosecutor. And now, if we calculate the sender's expected utility, the sender's expected utility is going to be 0.3, because with probability 0.3, the true state is going to be guilty, and the judge will take the action of convict. And that's the only case the sender will get a positive utility. And the judge's expected utility now becomes 1, because the judge always makes the correct decision for the defendant. And comparing with the previous case, so the sender's expected utility moves from 0 to 0.3, and the receiver's expected utility moves from 0.7 to 1. Okay, so that's fully revealing. And now think about the sender. Doesn't really care about increasing the receiver's expected utility. The sender really just wants to increase his own expected utility. So then the question is that, can the sender pick a different signaling scheme and do better? Do better means that the sender's expected utility is going to be higher. And the Bayesian persuasion problem is essentially the problem of finding the optimal signaling scheme of the sender to maximize the sender's expected utility. And in this case, the optimal signaling scheme for the sender is to signaling or to send a recommendation of convict with probability 1 whenever the true state of the word is guilty. So whenever the defendant is truly guilty, we'll always send a recommendation of convict to the judge. But when the true state of the word is innocent, the sender actually will randomize between 2 possible recommendations. So the sender will recommend acquit with probability 4/7 and recommend convict with probability 3/7. So in this case, after the judge is observing a realized signal, the judge will update his beliefs. So whenever the judge observes the recommendation of acquit, the A, because the only case A got sent is when the true state is innocent. So the judge knows with probability 1 that the defendant is innocent. But the judge now is a little bit more uncertain when receiving the recommendation of convict. So when receiving the recommendation of convict, the probability for the defendant to be guilty is only probability of 0.5. Okay? But the judge will still, the judge becomes indifferent of taking the action of convict or acquit when receiving a recommendation of convict in this case. And if a break tie in favor of the sender, then what the judge will do is the judge will convict whenever receiving signal C and will acquit whenever receive signal A. This leads to even higher sender expected utility. Now the sender's expected utility moved from 0.3 to 0.6. The receiver's expected utility falls back to 0.7, which is the same as in the original case when there's no communication, no signaling, and the receiver will just make their decision based on the prior distribution. Okay? So this is a classical example of information design. In this setting, the sender is the one that has the informational advantage, and the receiver is the one who can take actions, because the sender can't take actions himself. Otherwise, he doesn't need to try to influence the action of the receiver. So I think the essence of this setting is that the receiver can take actions, but the sender has better information. And then what the sender can do to try to influence the receiver's action is by designing an informational environment to influence the belief of the receiver and eventually to change their action. Okay. And this is a good example for us to think about. What if we try to think about the misinformation setting of a social media platform? Does the platform have some informational advantage? So I think the things to think about for the Bayesian persuasion to work is that, so we do assume that the receiver is Bayesian, is the rational agents. So you can argue that that may not be the best assumption to assume, but we're going to carry that assumption forward. And it also assumes that the sender needs to commit to a signaling scheme a priori, and the receiver observes and knows that signaling scheme such that the receiver can do the correct Bayesian updating. It also assumes that the sender knows the receiver's utility function, because otherwise the sender won't be able to correctly calculate what's the best signaling scheme. But the key part really is that the sender has informational advantage. And if we're trying to think about a social media platform setting where the platform can act as the sender and has some informational advantage, it's actually more reasonable for the platform to satisfy some of these assumptions. For example, because the platform has repeated interactions with the users in the past, hence the platform probably have a very good estimate of the user's utility function. Okay. So if we're moving this line, we're basically asking, is it possible that we're using information design as an approach to reduce the sharing of misinformation? So here, we're taking the social media platform as the sender, and we're thinking that for every post, there is an unknown state of the world about the post. And just to match the misinformation setting, I'm going to just illustrate the state of the post as having two dimensions. You can think about that one dimension is the misinformation dimension that the platform cares more about. That's the M. And the other dimension is the mu, that is the popularity dimension. That is that if this post is actually being shared, how likely these are going to receive a lot of likes to become popular. That's probably what users on social media platform cares more about. But then if we really want to just do signaling, the sender needs to know the exact state of the world. And that's usually not reasonable. But what's reasonable to think about is that the platform have machine learning algorithms. So all the platforms do. They try to predict the state about a post. So the theta hat is representing the platform's prediction, and they're not necessarily always accurate, but we can think about that the accuracy of the classification algorithm be represented using a confusion matrix for the classifier. And the confusion matrix, each element is giving the probability of theta hat conditioning on the true state being theta. It's like how likely the prediction is wrong. Okay, so the confusion matrix. So if we're thinking, okay, this sounds good, but the standard Bayesian persuasion requires that the sender knows the exact state of the world. If we're thinking about the platform can only have noisy predictions about the state of the world, can the platform leverage the noisy informational advantage to persuade users to not share likely misinformation? So that's the question that we're asking about. And I think a related question, so this is usually important for the platform, is that the platform are updating their classifiers all the time. So essentially, they do have the option of improving the classifier over time, and then the confusion matrix of the classifier are going to change. So suppose we can do optimal signaling with a noisy prediction theta hat. So under a different confusion matrix, how does the change of the confusion matrix changes the effectiveness? So basically, we want to understand how does different Q leads to different persuasion outcomes in this setting. So that's where we're coming from. We're essentially inspired by the Bayesian persuasion by leveraging, so one agent leveraging the informational advantage to influence the action of the other agent. And we try to think about whether we can extend that into a noisy persuasion setting such that we can apply the information design approach to reduce the sharing of misinformation. Now let me give the model. So I want to talk about the model, and I will give the key result that we have achieved, we managed to obtain. There are still some open questions, but I also want to give some intuition, some geometric intuition of why the results hold that way. So I will not give any formal proofs, just the geometric intuition. But hopefully, at this point, I've at least to communicate enough information such that you think it is the sensible way that we can use the information design approach to model the sharing of misinformation. So our specific model is that we're considering two players. Player one is the sender, is a social media platform. And player two is a user on the platform who has drafted some content, is considering sharing, okay? And then the unknown state of the world is the state about the post, so which is the true misinformation state and the true popularity state. We actually don't assume this states being binary, so we do allow that there's different levels of misinformation, different degrees of misinformation, and similarly different degree of popularity. So the cardinality of the state are not restricted to two. And then platform and the user has a shared prior over, which is the probability distribution over the state. And you can think about that for social media platform. The user has interacted with the platform in the past over a certain period of time, and that will help them to form some common prior based on the post that they shared, how many has become popular and how many has been considered to contain misinformation. Okay. And the user's action space is binary. So we will do assume that the users can only take one of two actions, that is share the post or not share or discard the post, okay? And then user utility is generic. That depends on the true state of the post and the action that the user takes, the share or not share. And the platform utility also depends on the true state of the post and the action that the user has chosen to take. Okay. And then we have the noisy persuasion part, because the platform do not actually observe the true theta but only using some classifier to give a prediction of theta hat. So the platform only knows about the theta hat, but the platform can do signaling based on theta hat. So essentially, the platform can specify a signaling scheme that is the probability distribution of sending a set of signals conditioning on a predicted state. Okay? And usually it is without loss of generality to think about the space of the signal as just the space of the actions, because the platform can always just recommend an action to the user or to the receiver, and at an equilibrium of this two-player game, the user would find just following that recommendation and taking that action is the best thing for the user to do. Okay. And the user can do Bayesian updating and choose the optimal action accordingly. Okay. So let me just give the timeline of the interaction. So the user and the platform, they have shared some prior. So the platform will first commit to a signaling distribution, which is this pi. And then the user drafts a post and considering whether to share or not. And given the post, the platform can apply the classifier and make a prediction on the state, so get the theta hat. And then the platform will just draw a signal according to the committed signaling scheme and send the signal to the user. The user observes the signal. Now the signal can be viewed as an action recommendation. So the user, also knowing the signaling scheme, will update the belief about what's the likelihood that the post is of a particular true state. And then the user will take the optimal action given his updated belief. So that's the interaction timeline. Okay. So, question?
Can the same timeline be applied to safety on platforms like platform activity like user safety to combat bullying and stuff like that in common settings?
Yeah, I think if you think about the action or not share, the action or some other action that's related to the safety, user safety, this definitely apply to that too. So it's just we're taking kind of like reducing the sharing of misinformation as an application example to illustrate the noisy persuasion problem. So you can definitely think about that. The platform has a classifier trying to classify whether the content is safe content or not. And depending on that, it makes a recommendation for the users to take certain actions. But the key point is that I've been saying that this is a softer approach. The reason that we believe this is a softer approach is the action is still taken by the user, and the user is still taking the best action given his knowledge or given his belief.
So I guess as a corollary, if someone wanted to spread misinformation, this would not deter them.
This will not deter them. So in some sense, if the platform's utility is the more misinformation on my platform, the better, then this will only help to promote misinformation. So you're right. I'm taking a very benign assumption for the platform. I'm assuming that the platform doesn't like having a lot of misinformation on the platform. The user doesn't necessarily, the user could be indifferent or even prefer misinformation. Okay. Yeah, so information design, when facing a Bayesian rational agents, the bottom line is that it will never reduce the user's expected utility. So because you just can't really hurt a Bayesian agent by providing more information to the Bayesian agent. So that's the bottom line. So you can never hurt the receiver in terms of its expected utility. In the early judge example, even in the optimal a signaling case, the judge's expected utility is the same as without any communication. So the receiver can never be hurt. And what can be improved really is the sender's utility. And if the sender prefers a lot of misinformation on the platform, this is a terrible idea for the sender to do information design.
So can I actually look at the problem in a reverse way? So let's say I am an adversary, and the platform can actually do executing power and block the post if they know that it's going to be misinformation. So can I actually use this in my, so I do know that I'm trying to publish misinformation, but then I can play the role of adversary and pretend or convince the platform that this is not a misinformation, even though it is a misinformation. I'm trying to increase the utility of the platform, even though I am trying to post a misinformation. This can also happen, right?
Yeah, so if I think if you really assume that the users has more information about the post than the platform, and the user can influence the platform's decision about whether banning this post or not, yes, I think this is also possible. So that's a really good point. So this can go the other way too. If the user really is an adversary and has a lot more knowledge about the content of the post and try to spread it. So the user can also try to do that. But the issue with that, then it becomes a little bit unreasonable to say that the user commits to a signaling scheme to the platform. So I think it's more reasonable when, as the operators of the platform will say that this is my signaling scheme to all users and commit to that. And a user who just occasionally submit a post, like when submitting a post, at the same time commit to a signaling scheme is a little bit like a weird in practice. Yeah. So, yeah. Okay. So I want to just give you an example for the combating misinformation setting, just to get a sense of what the utility may look like. So this example actually doesn't give a lot more information beyond what we have shown in the early example, except that it captures what the noisy persuasion looks like and what the platform and the user utility function may look like in the social media platform setting. So we said that we have the true state, and we're thinking about like a two-dimension of a misinformation state and popularity state and binary user action. We can think about the common prior shared by the user and the platform about the true state of a post. Something looks like this. But essentially what it's saying is that the post will have a popularity with probability 0.5 and being unpopular with probability 0.5. It's more likely to not contain misinformation with probability 0.7, and with probability 0.3, it may contain misinformation. And in this example, I'm using just a binary misinformation state and popularity state, but that's not the restriction that we have in the model. Okay, and then let's look at the not completely aligned user and platform utility, because when their utility is perfectly aligned, there's no need to do persuasion because the best action for the receiver is also the best action for the sender. So only when their utility are not perfectly aligned, there's room for improving the sender expected utility through persuasion. So let's look at the user. So the user is actually the receiver. So the user can take the action of sharing, so share or discard. And clearly, if the post is popular, sharing will bring utility 1 to the user, regardless of the true, like a misinformation state, whether the post has misinformation or not. And if it's unpopular, he regrets about sharing. It has negative utility. And when the user chooses to not share, discard, and if the post is popular, he regrets not sharing. And if it's unpopular, he receives 0 utility. But the key point of this example is that the user doesn't care about the misinformation state. So he's perfectly happy about sharing anything that's popular, regardless whether it contains misinformation or not, okay? And on the other hand, the platform does care about misinformation. So when the user chooses to share, so when the post doesn't contain misinformation and it's popular, it gets the highest utility for the platform. Even when it's unpopular, it still gets some positive utility because it's a post without misinformation. But with misinformation, sharing creates negative utility for the platform. So essentially, the platform utility is aligned along whether it contains misinformation or not, where the user's utility is aligned along the direction of whether the post is going to be popular or not. And similarly, the platform's utility when the agents choose to not share is almost zero everywhere, except that when the post is popular and also doesn't contain misinformation, the platform will regret. Okay. So in this example, so we can calculate the user's decision just using the prior information. So the user's expected utility of sharing is 0. And the user's expected utility of discard the post is -1. So the user would prefer to share. And the platform's expected utility of sharing is 0.45. And the platform's expected utility of not sharing, for the user to not sharing, is -0.35. So the platform, in this case, without any information, will think that the user sharing the post is good for the platform. So that's what the user would choose to do without any additional information. And by doing this, about 30% of the post on the platform contains misinformation. So that's because the prior of post to contain misinformation is probability 0.3. Okay, but with noisy persuasion, so what the classifier can do is the classifier doesn't know the true state. The classifier only observes the theta hat, the predicted state. But essentially, based on the prior, the classifier also knows the likelihood of observing a predicted state. And the classifier can do some signaling. So for example, it would deterministically recommending sharing when the predicted state is true and unpopular, and true and popular. And it will deterministically recommend discard when the predicted state is false and unpopular, and it will randomize, create some confusion when the predicted state is false and popular. So I'm not going to do the calculation, but in this case, the expected utility for the platform becomes 0.64. And only 17% of the post on the platform contains misinformation. So this is just an example of saying that when we're thinking about that the platform and the user have misaligned utility, and the user doesn't care about misinformation, the platform does care about misinformation. This is an example of showing that noisy persuasion can improve the platform's expected utility and reduce the amount of misinformation on the platform. And I want to just comment that this is actually the hardest case for the platform to do the persuasion because the user's utility is completely unaligned. The user doesn't care about misinformation at all. If the user also to a certain degree care about misinformation, then the amount of misinformation on the platform will only be further reduced. Okay, so now let me just quickly tell you about so I have found 2 for 30, right? Okay, great. The result that we get, I'm not going to go into the technical details. The first question naturally is that what is the platform's optimal signaling scheme given a classifier? So we answer this question by saying that we can solve for the optimal signaling scheme using a linear program formulation. Okay? And the second is that is there ordering of classifier accuracy with respect to optimal platform utility? So we give a strict ordering with respect to symmetric confusion matrix on this question. And the third question is that if the platform improves its classifier, so the confusion matrix changes, how does the optimal platform utility change with respect to that? And the answer that we have is that, oh, it's going to change continuously with the change of the confusion matrix. So the expected optimal platform utility is Lipschitz continuous with respect to the platform confusion matrix. So I want to skip the first one because it's really just to give you an LP formulation and nothing else. I want to jump to the second and the third one to explain our result. And then what I'm hoping to do is that I want to have 2 slides to actually give some geometric intuition of what's going on here. So what are we doing? So let me just jump through the LP formulation because it's really just a linear program. So the second question is there an ordering for classifier accuracy with respect to optimal platform utility? So we would expect that more accurate classifier or better classifier will lead to higher optimal utility for the platform. But better in what sense? So false positive rate, false negative rate, or some other criteria. And the result that we got from symmetric confusion matrices, so notice that we were only able to get the results when the confusion matrices are symmetric, is the following convex Hall conclusion result. That is, if we have 2 confusion matrices, Q1 and Q2, so Q2 is better in the sense of when the platform doing optimal signaling given Q2, the expected platform utility is going to be higher compared with the expected platform utility when the platform doing optimal signaling under Q1. So that's what we mean better. So the platform's expected utility are going to be higher. So this is only true. So if and only if a convex Hall inclusion relationship is satisfied. And this relationship basically says that if it takes the rows of the confusion matrix and look at the convex Hall of the rows, then the convex Hall of the rows of Q1 is a subset of the convex Hall of the rows of Q2. And if that's true, Q2 is better, okay? And while this may feel a complicated condition, but it's actually a really easy to check condition. What this says is that every row of Q1 belong to so can be written as a convex combination of the rows of Q2. So it belongs to the convex Hall of Q2. So it's a very clean condition and it's also very easy to check, okay? So that's regarding to the impact of the Q on the ability for the platform to do optimal signaling, okay? And we're also curious about like, what if the platform changes the Q slightly? Is that going to lead to a drastically different outcome? And what we show is that it's actually almost always true that the optimal platform utility is Lipschitz continuous in the confusion matrix. Okay. So I'm not going to go into the proofs, but I do want to give you some geometric intuition because this is what I find really interesting about the insights of Bayesian persuasion. So if we're thinking about the original Bayesian persuasion, so here we're not thinking about the noisy Bayesian persuasion yet. So essentially what's going to happen is whenever the sender chooses a signaling scheme, because a signaling scheme is a distribution over multiple signals. So now let's just think about that. We have binary state and binary signal for the purpose of illustration. So the signaling scheme is a distribution over 2 signals. And then what the receiver will observe is a realization of a signal. So either signal 0 of signal 1. And after receiving a signal, the receiver are going to have a posterior belief where we denote it as rho s theta here about the true state of the world. So essentially, a signaling scheme is choosing a distribution over two different posterior beliefs. And because we're in the Bayesian framework, so this posterior belief have to be constrained by something called Bayesian plausibility, because we do have a prior. So what it's saying is that, okay, we start with a prior, and now we're thinking about a decomposition of the prior into some posterior beliefs, such that whenever we send probability, we set signal with probability, signal S with probability S, and we have the posterior of rho S, summing across all signal, this should give back to the prior. Because this is just the Bayesian requirement. Whenever we're doing things with Bayesian, everything has to be the expectation of the posterior belief must equal to the prior. But then geometrically, what does this mean? So now we're talking about binary states. So I have between the state between 0 and 1, okay? And then my prior, let's just say that, my prior is here. My prior is mu. My prior is the probability of the state 1, of the state 0, let's say of the state 0, okay? And then I have different ways of decomposing this prior into posteriors. So I can decompose this prior into two posteriors, one on the left and the other on the right, okay? And then the probability for sending this signal 0, so this is the posterior after the receiver receives signal 0, is just the relative distance between this mu and the other one relative to the total distance. Right? So since this is 1, this is really just this distance times this prior, this posterior, plus this distance times this posterior. So what it's saying is that the prior is decomposed into a convex combination of two posteriors. And I can decompose that in whatever way, as long as one posterior is to the left of my prior and the other posterior is to the right of my prior. So that's a valid decomposition. So now the question of choosing the optimal signaling scheme is to choose the optimal decomposition of the posteriors for the receiver. Okay. And why that's helpful? Because for the receiver, given a posterior, the receiver are going to have an optimal action. And we're having only two actions. So which means that there is a posterior belief, the receiver will be indifference between two actions. So to the left of this belief, when the receiver has a belief along this region, the receiver are going to take action 0, for example. And when the receiver has a belief to the right, the receiver are going to take action 1. So that's the receiver's optimal action. But then we care about the sender's expected utility. But we know that whenever the receiver has this belief along here, the receiver are going to take one action. Then we can plot the expected utility for the receiver with respect to the belief of the sender. And that's going to look like something like this. Okay? And there's a discontinuity here because the action changes. So we can have such discontinuity. But now if I think about what's the best way of decomposing the prior into two posteriors, we care about the expected utility for the receiver. And when there's no persuasion, the receiver will receive this point as the expected utility. But when we're decomposing, because mu is a convex combination of the two decomposed posteriors, And when the receiver has this belief, the sender will have this expected utility. And when the receiver has this belief, the sender will have that point as the expected utility. And the expected utility of the sender is a convex combination with the same probability. So that's going to be this point, landed there. So the characterization is actually the possible optimal expected platform utility with, so here with exact persuasion, lie on the concave closure of this function. So the concave closure is the smallest concave function that can cover the blue curves. Okay? And hence, the platform's optimal utility will be this mu star corresponding to the prior on this line. So that's the intuition of Bayesian persuasion, why it works, because it essentially allows the platform to achieve a convex combination of two expected utilities that's higher than before. Okay, but then what about our noisy persuasion? So our noisy persuasion has to be worse than the exact persuasion. And the reason that it's worse is essentially because of the inaccuracy of the classifier. We're shrinking the possible beliefs that the sender can induce the receiver to have. So now the sender can only decompose the prior to the range from here to here. So the decomposition range is smaller, and then the concave closure of what can possibly be decomposed will be lower. And hence that the platform utility is also lower. Okay, so we ran some synthetic experiments. So I think it's not so important for us to go over this, but I just want to mention that even when very inaccurate, even when the classifier is very accurate with a classification error of 0.4, the amount of misinformation decrease can still be around 10%, okay, in these experiments. So I want to stop here. I want to quickly mention that we also look at performative model because the prior depends on the percentage of the post that contain misinformation in the platform. Since we're changing the sharing behavior, we're also changing the prior. So we're looking at a performative model to say that then how does this performative process converges to a state and what's the amount of misinformation at that state? I just mentioned that, but let me stop. So I think there are some immediate open questions. That is the ordering of classifier with general confusion matrices. We don't know about that. But I think the bigger open questions is that whether this really works in practice. And we're hoping that we can collaborate with some companies to do field tests for this approach. Let me conclude by saying that if we want better information, we need to take into consideration of human behavior because we are generating information and we're responding to the environment and the classification rule and the platform decisions. Okay. Thank you very much.
Yeah, so we'll take questions from the room and shall we, Zoom questions should be on chat.
Yes, no one's asked anything yet.
Okay, so maybe you can let us know.
Yes.
But yeah, Yiling, take questions.
So let's pose the question of say I have two platforms. There is no agent involved, and both platforms can provide signal to each other. So let's say I have Facebook and there is another company which is inside the Facebook. So now they should interact. So to reach a consensus, right? It's not only the signaling goes one way, you can actually have the signal going the other way as well. So I can actually provide also signal to the platform and we can have these feedback. I think was also related to one of the slide issues. So this gets now more challenging, right?
Yeah,
because
this
more open loop, provide the signal and then just it's easier, it becomes linear programming, but in this case, it can get more complex, right?
Yeah, so I think that's a great question. So I think I was actually thinking about a slightly different version of your question. So because one very natural way would be that there are two platforms, both try to influence an agent to take some actions. Because for persuasion to work, we need an agent who actually are taking actions. So if we just have two platforms, then maybe both platforms can take certain actions. But what I want to say is that, so multi-sender persuasion is incredibly challenging. So we actually recently started a model with multi-sender persuasion. And so the theoretical side of the things is that it is even computationally hard to compute a best response to a strategy. But the good side is that there are computational approach that we're doing pretty well. Okay, so I think it's definitely going to get more interesting and more challenging. And I would say that the analytical approach probably doesn't work. We'll have to take a more like a differential economy type of approach by taking some computational method to do that.
So there's not agreement about what misinformation is. And the platforms don't care that much about the presence of misinformation on their platform. Like their primary goal is engagement. And there's this issue, natural engagement goes up with the toxicity or disconnect from reality, as it were. And so their metrics don't really want all of their posts to be right on that line of where they need to moderate the content.
Yeah.
But they want to benefit from the engagement on that, increase for posts that are very close to it.
Yeah.
But then they have substantial power to see who sees the posts. And so none of the commercial platforms are kind of only making the binary choice of whether the post is moderated or not.
Yeah.
But rather specifically who they promote to when in order to kind of drive that engagement.
Yeah.
But within that context, like if we as society believe that misinformation going wild on the platforms is bad, where do you see as like the lever or model for?
Yeah, that's a really great question, because I think this work takes the assumption that the platform doesn't like misinformation on the platform. And I think what you said, there is definitely a degree of truth there. The platform probably doesn't like a reputation of the platform has a lot of misinformation. But when it's very difficult to decide whether what's out there is misinformation or not, it may enjoy the popularity a little bit. So it's not a clear cut that the platform's utility is definitely that I want to reduce the misinformation to zero. So I agree with that. I totally agree with the reality. So I guess that I have several like perspectives for this question. So one is that I do think misinformation is not a black and white thing. So whether something is misinformation or not is arguable. That's also why I think a lot of platform doesn't like a very harsh, like approach of saying that I determine this post is misinformation, hence I'm not sharing with you. And that's why a softer approach might be more helpful. So that's along which I totally agree, and which also is consistent with where we're thinking that the platform only make a prediction of what's likely. And the second thing is that if misinformation is not something that the platform absolutely want to reduce to zero, so I think the commercial platforms take safety very seriously. The contents that's being classified as harmful or potentially concerning, so they took that very seriously. They actually spent a lot of engineering effort trying to classify contents. And because they care about the accuracy of their classifier so much, they don't want to mistag a content. So they want the accuracy of the classifier to be really high before they take action. So they usually miss the initial phase of the misinformation being shared, because once they have already get a very accurate prediction, the posts have already been shared. So I think the benefit of this approach is that it's not to replace any other approach. This can be used in conjunction with other approach. And even if you have a not so accurate classifier, by doing this can still help a little bit. Yeah, I guess I don't have a good answer to what the government can do if the platform completely don't care about misinformation. Yeah, I think in that case, we probably should have some like legal consequences for the company. Yeah, I don't immediately have any softer like approach. Yeah, yeah.
Yeah, I'm sure there'd be more questions that people would like to ask, and for those in the room, come down and chat a bit more with Yiling. But we have to close the formal portion now, so thank you again.
Thank you very much.